Hi guys, it's Mrs. Millicent. We are going to do the check your understanding on page 560, which is a 1 proportion z-test, but I'm going to use an alternate example than the one in the book. Okay, the one I'm going to use is, a recent commercial claims that 9 out of 10 doctors recommend aspirin for a headache. You're not sure this is true since you never take aspirin. You either take Tylenol or Motrin for headaches. So therefore, you decide to do a little research. You randomly select 100 doctors and ask them if they recommend aspirin for a headache. 82 said they did. So in your sample proportion is 82 out of 100. Okay, we're going to compare that to the population proportion, which is the claim, which is 9 out of 10. Okay, now sure, these are different, okay, but are they significantly different? Okay, or is this pretty much the same thing as that? Okay, so that's what a significance test is going to allow us to do, is compare these two statistically. Okay. All right, so we have to go through our state, plan, do, and conclude, just like with a confidence interval. For the state section, the first thing we're going to do is identify what it is we're testing. So we're going to identify P, which is the true population proportion of doctors who recommend aspirin for headaches. Oops, headaches. Okay, so we're going to state our hypotheses. So we have to start with our null hypothesis, which is H sub O, which I will fondly refer to as the HO. And this claims that the true population proportion of doctors who recommend aspirin is 0.9. Okay, so this will always be our population parameter, or the thing that we are testing. Okay, the claim we're testing. Our alternative hypothesis, which I'll call the HA, is going to kind of argue with this claim. We say, since our sample is less, we're going to say we think the true population proportion of doctors who recommend aspirin for headaches is less than 0.9. Okay, so this sign should follow the value of your p hat. Okay, now this is a one-tailed test, greater than or less than our one-tailed test. We could also say that p does not equal 0.9 if we just think it's different. Okay, and sometimes the wording in the question or the wording in the problem will lead you to make this a p is not equal to 0.9. Okay, for this case we're going to do less than. Okay, we are going to test our hypotheses at an alpha level of 0.05. Our different alpha levels are anywhere from we usually do 1%, 5%, or 10%, and we talk about those differences in class. Okay, so we're done with our state section. Let's do our plan, and our plan section is pretty much exactly like the plan section in a confidence interval. So first thing I have to do is state my inference method, and I'm going to do a 1 proportion z test as opposed to a 1 proportion z interval. Okay, conditions are the same. So random, yes, it was definitely stated. Stated randomly selected doctors. My independence, okay, I'll do my 10% rule. Pretty sure there's more than 1,000 doctors. Remember, this is 10 times n. My sample size was 100. And, of course, doctors are independent of each other. Okay, last condition is normal. And since these are proportions, I've got to use large counts, which again is n times p is greater than 10, n times 1 minus p is greater than 10. So now I've got a p back. When I did my confidence intervals, I didn't have a p, I had to use p hat. Well, now I got a p because my p is 0.9, so that's what I'm going to use here. So let's see, 100 times 0.9, which is 90, is definitely greater than 10. Ooh, 100 times 0.1 is 10. That's okay, 10 is greater than or equal to 10. So that condition is met. Yay. Okay. Plan's done. Let's do the do. Okay. So now we've got to basically z-score. Okay. Because if you think about it, this is what we're doing. We're taking our normal curve, our mean is 0.9. The mean of our sampling distribution should be the true population mean, right? And then we're comparing 0.82 to it. Okay, and we want to know if it's significantly less. So there's the one tail. Okay, if we did a not equal to, I would have something over here and I would have this shaded, a two-tail test. But this is my one tail of my one-tail test. So basically we're just going to z-score it. Okay, so we're going to say z equals x minus the mean over the standard deviation of the sampling distribution. Okay, well the mean is 0.9. That's the mean of my sampling distribution. Standard deviation of my sampling distribution is that. Okay, we're used to seeing that. So what goes here is my sample. Okay, my sample proportion. Excuse me. We throw that in the calculator. I believe it's something like that. Okay. And then, of course, we normal, oops, let me move this up a little bit. We normal CDF that, and I'm going to go from negative infinity to negative 2.667. And that's my probability or my p-value. Okay, so my p equals 0.0038. Okay, so that p-value is the probability that my sample would have just happened by chance. So that's pretty small. I doubt that that happened by chance. Okay, so something had to have made that happen. Okay, so what we do for our conclusion is we test our p against our alpha. So our alpha was 5%. Since this is true, we can say our p is low. Compared to our alpha, our p is low. So if our p is low, we can reject the HO. So we're going to reject that, and we do have evidence that the true population proportion of doctors who recommend aspirin for headaches is less than 0.9. Okay, and that is my conclusion. Let me write that out because that's a long one. Okay, so we're going to state the p-value 0.0038 is less than alpha of 0.05. Okay, and when it is less, it is statistically significant. So it is statistically significant. I'm trying to write small because I got a lot to write in this space. Okay, oh sorry. And again, that's a 5. We'll only write that when the p is less than alpha. When the p is greater than alpha, it's not statistically significant. So the p-value 0.003 is less than alpha of 0.05, so it is statistically significant at the 5% level, which is coming from my alpha, so we can reject the HO, reject the null hypothesis. Okay, so if we reject the HO, if we reject the null hypothesis, I do have evidence that the HA, or the alternative, is true. So I'm going to say that. Oops, sorry, let me move my book up. We have, sorry, I got to lean against my book. We have convincing evidence that the true population proportion of doctors who recommend aspirin for headaches is less than 0.9. Okay, so really all I did, give you a second to look at that, all I did in this sentence right here is read the alternative hypothesis but fill in what p equals. Okay, so again, since the probability that this would have just happened by chance is so low, okay, that something had to have made it happen. So therefore I will reject the HO, and I will say I do have evidence that the true population proportion of doctors who recommend aspirin for headaches is less than 0.9. Okay? So that is our one proportion z test in a nutshell. Let me show you. Let's run it on the calculator real quick because we're going to double check everything. Okay, so in the calculator, I can run my significance test. So if I go to stat, over to tests again, this time we're going to look for one proportion z test. Okay, so the first thing I have to put in there is the proportion for my hoe. See the little sub-zero? So of course my proportion for my null hypothesis is 0.9. What was the x over the n for my sample? Well, that was 82 over 100. And then down here I'm going to put the sign of my alternative hypothesis. So I did less than. Okay, I always like to draw. I don't know, it's just fun. That looks like my picture. So I'm going to draw it, and it should look just like my picture. And lo and behold, if you look real close, the z, the critical z, right, or excuse me, the z-score is negative 2.667, and the p-value is 0.0038. So I totally agreed with the calculator, or rather the calculator agreed with me, so I know I'm right. So my p is low, I can reject the hoe, which means I have evidence for the ha. Okay, that's it for one proportion z test. See y'all later.